Have you ever wondered who is the most famous physicist ever? Or have you ever wondered who is the father of quantum mechanics? Then in this video, you will get to know about the great physicist Max Planck. Max Planck changed the face of physics in the 20th century with his revolutionary idea of quantized energy. But there are some lesser-known facts about him that might surprise you. So let's dive into the life and work of this brilliant mind. Max Planck was born on April 23, 1858, in Kiel, Germany. His father, Johann Conrad Planck, was a lawyer, and his mother, Emily Beckenbauer Planck, was a homemaker. When Max was 6 years old, the family moved to Berlin, where he grew up. From an early age, Max showed signs of being a highly intelligent person. He displayed a strong interest in science and mathematics and was also a gifted musician. In fact, it was his mother's singing that inspired him to become a scientist. As a child, he would listen to her singing and became fascinated by the way sound waves could be both a physical phenomenon and an aesthetic experience. However, his mother died when he was only 17 years old, which had a profound impact on him. Despite this personal tragedy, Planck went on to study physics at the University of Munich and later at the University of Berlin. In 1878, he received his doctorate from the University of Munich with a thesis on the second law of thermodynamics, and after that, he began working as a professor at the University of Munich. Though Planck made significant contributions to various areas of physics, including thermodynamics, electromagnetism, and optics, he is best known for his work on quantum theory. It all started when he was trying to explain blackbody radiation, which is the electromagnetic radiation emitted by an idealized object that absorbs all radiation incident upon it, regardless of frequency. Classical physics was unable to explain the observed spectrum of blackbody radiation, which showed that the intensity of radiation at a given wavelength depended on the temperature of the object. The issue was that classical physics predicted that the intensity of light should increase at higher frequencies, but this was not observed experimentally. Planck resolved this problem by proposing that energy is quantized, meaning it can only exist in discrete amounts, or quanta. This revolutionary idea marked a paradigm shift in physics and laid the foundation for the development of quantum mechanics. Before Planck's discovery, physicists believed that energy could take on any value. However, his groundbreaking work demonstrated that energy is quantized, meaning it can only exist in specific discrete amounts. This revelation led to the development of quantum mechanics, which studies the behavior of matter and energy at the atomic and subatomic level. One of the key concepts in quantum mechanics is the idea that particles like electrons can exhibit wave-like properties. This concept, known as wave-particle duality, was first proposed by Louis de Broglie in 1924. However, it was later confirmed and expanded upon by experiments conducted by scientists such as Davison and Germer, who demonstrated that electrons can diffract, a phenomenon that is characteristic of waves. These experiments provided evidence for the wave-like nature of particles, which is a fundamental concept in quantum mechanics. Furthermore, scientists such as Werner Heisenberg and Erwin Schrödinger developed new mathematical tools and frameworks to describe the behavior of particles in terms of waves, leading to a more comprehensive understanding of quantum phenomena. Planck's most famous equation, E equals hn, represents the relationship between the energy of a photon and its frequency. In this equation, E represents the energy of a photon, h is Planck's constant, and n is the frequency of the radiation. This equation is one of the most important equations in physics because it shows that energy is quantized. Before Planck's discovery, physicists believed that energy could take on any value. However, this equation demonstrates that energy can only exist in discrete amounts. The significance of this discovery cannot be overstated. It marked a paradigm shift in our understanding of the nature of reality and laid the foundation for the development of quantum mechanics. By showing that energy is quantized, Planck opened up a whole new world of possibilities for understanding the behavior of matter and energy at the atomic and subatomic level. Besides explaining blackbody radiation, Planck's quantum theory had a profound impact on other areas of physics, including the photoelectric effect and atomic structure. The photoelectric effect is the emission of electrons from a metal plate when light shines on it. Classical physics was unable to explain why the electrons were emitted only when light of a certain frequency was used, even though the intensity of the light was increased. Planck's quantum theory provided a solution to this puzzle by proposing that light is quantized into photons, each carrying a discrete amount of energy. This explained why the electrons were emitted only when light of a certain frequency was used, since the energy of the photons must be above a certain threshold to dislodge an electron from the metal plate. Similarly, Planck's quantum theory also helped to explain the structure of atoms. According to classical physics, an electron could spiral into the nucleus because it would emit electromagnetic radiation and lose energy continuously. However, this did not agree with the observed stability of atoms. Planck's quantum theory resolved this issue by proposing that electrons occupy specific energy levels or shells around the nucleus and can only transition between these levels by absorbing or emitting photons of specific energies. This model of atomic structure laid the foundation for the development of quantum chemistry and our understanding of chemical bonding. The impact of Planck's discovery on the scientific community was immediate. His contemporaries recognized the profound implications of his work and praised him for his contributions to physics. Albert Einstein was one of the first to recognize the significance of Planck's discovery. He realized that Planck's quantum theory could be applied to the photoelectric effect and used it to calculate the energy of a photon. This application of quantum theory to the photoelectric effect earned Einstein the Nobel Prize in Physics in 1921. Another scientist who recognized the importance of Planck's work was Louis de Broglie. He extended Planck's ideas to propose that all matter has a wave-like nature, and this concept led to the development of wave mechanics. Louis de Broglie was awarded the Nobel Prize in Physics in 1929 for his discovery of the wave nature of electrons. But unfortunately, it was not until 1918 that scientists began to fully appreciate the significance of Planck's work. That year, he was awarded the Nobel Prize in Physics for his services to theoretical physics, particularly for his discovery of energy quanta. This recognition cemented his place in history as one of the most important physicists of the 20th century. Today, Planck's contributions to physics are still celebrated, and his legacy continues to inspire scientists around the world. The unit of action, Planck's constant, is named after him, and his image appears on the euro banknote. His work laid the foundation for some of the most important developments in modern physics, including quantum mechanics, quantum field theory, and quantum computing, and his ideas have had a profound impact on our understanding of the nature of reality. As we continue to explore the mysteries of the universe, we can be inspired by Planck's courage to question the status quo and his dedication to uncovering the fundamental laws that govern our world. But Planck was not just a brilliant physicist, he was also a complex and sometimes controversial figure. During World War I, he supported the war effort and served in the German army. This caused a rift between him and some of his colleagues, such as Albert Einstein, who opposed the war. Additionally, Planck was a vocal critic of what he saw as the excesses of theoretical physics in the years following World War II. He believed that the emphasis on abstract mathematics and speculation had come at the expense of experimental verification, and that this trend had led to a decline in the quality of research. Despite these controversies, Planck's contributions to physics are undeniable. His work laid the foundation for some of the most important developments in modern physics, and his ideas continue to inspire scientists around the world. Planck died on October 4, 1947 in Berlin, at the age of 89. He left behind a legacy of scientific excellence and a deep understanding of the fundamental laws that govern our universe. I hope you found this video informative and enjoyable. If you did, please don't forget to leave a like and subscribe for more videos on great scientists. And if you have any feedback or suggestions, feel free to comment below. Thank you for watching, and I'll see you in the next one.